This example comes out of section 6.2, some difference in double angle identities. So one use of these identities is to do something like this, where it says find the exact value of cosine of 15 degrees. Now cosine of 15 degrees is not a number that you would usually have the exact value memorized for. You could punch it into a calculator and it'll tell you that cosine of 15 degrees equals 0.9659258 decimal. No matter what you do with that number on a regular TI-83, 84 calculator anyway, you can't convert it into fractions or exact values. So one use of the identities we just talked about, the difference identities, would be to say, well, if I know two angles that add or subtract to give me 15, and two very simple angles do 45 and 30, if you say 45 minus 30, you get 15. So the identity for subtracting in a cosine function is cos A minus B equals cos A cos B plus sine A sine B. Now, if I replace A and B with 45 degrees and 30 degrees, I'm going to end up with cos of 45 degrees times cos of 30 degrees plus sine of 45 degrees times sine of 30 degrees. Now hopefully you've got enough knowledge of a unit circle that you know these first couple of coordinates on it. At 30 degrees we've got root 3 over 2, comma 1/2. And at 45 degrees we have root 2 over 2, comma root 2 over 2. What that lets me do then is say, well, cos of 45 is root 2 over 2, cos of 30 is root 3 over 2, sine of 45 is root 2 over 2, and sine of 30 is 1 over 2. Multiply these out, I got root 2 times root 3 is root 6, all over 4, and then root 2 times 1 is root 2, also over 4. To add fractions I need to common denominators, but I already do. Denominator is 4, and so I've got root 6 plus root 2 divided by 4. And that exact value, you can punch it into your calculator to test, but it will give you the same 0.9659226, however many decimals you want to write. Second one that we'll try with this is what's tan of 105 degrees. A very similar type of question. I don't expect any of you know what tan of 105 degrees is, but we do know that 60 plus 45 equals 105, so we can set it up as a sum question. Tan of 60 plus 45, if I write down the identity, I've got tan of A plus B equals tan A plus tan B divided by 1 minus tan A tan B. Now, tan of 60 plus 45 in particular is equal to, I need to know a little bit more about 60 and 45. So if I draw myself a unit circle over on the side again, I already had the points for 45 a second ago, root 2 over 2, root 2 over 2. At 60 degrees I've got 1/2, comma, root 3 over 2. Now, tan isn't one of those coordinates. Tan is sine divided by cosine. But if I take a look and say, well, if I know tan is sine divided by cosine, tan of 45 is equal to 1. That might be one of the only tangent ratios most people get to know off by heart. Tan of 60, you just have to do root 3 over 2 divided by half. And if you simplify that, you get root 3. So if I start putting in numbers here, tan of 60 is root 3, tan of 45 is 1, 1 minus root 3 times 1 equals root 3 plus 1 over 1 minus root 3. That's the true answer. That is an exact value answer for tan 105. Quite often they'll ask you to rationalize an answer like that. So you've got root 3 plus 1 over 1 minus root 3. And if I want to rationalize this, I'm going to multiply by the conjugate of the denominator. Multiply by 1 plus root 3 on the bottom and on the top, which means I'm not changing the value. The beauty of the bottom is you end up with 1 minus 3, which is negative 2. On the top I end up with root 3 plus 1 plus root 3, which ends up giving me 2 root 3 plus 4 over negative 2. If I factor the top, I can take out a 2, divide everything by negative 2, I end up with negative root 3 minus 2. And if you try that on your calculator, it gives you another irrational, terrible-looking decimal. This would also be useful, these identities, for example, if I was asked to do sine of 5 pi over 12, I strongly suggest if you're asked to do a question like that, that you change 5 pi over 12 into degrees and realize that this is sine of 75 degrees, which you could use an identity, say 45 plus 30, and carry out steps just like we did above. Doing it in radians requires you doing some pretty hefty fractions, common denominators, pi over 6 plus pi over 4 equals kind of stuff in your head. A lot easier to do that in degrees than in radians.